All right, so I'll get started. So the idea a little bit of this session, we've done the webinar together about a month ago, something like this. And we did to replay this here a little bit by doing like a back and forth of he's the super expert, I'm getting to learn. So everything about quantum will be explained by Frank. But why are we here today, right? So there's something looming that we call the Q day. You know, Q day is the day where quantum computers, and then we'll explain how, where quantum computers allegedly will be able to decrypt what we know today as being the foundation of what we do in terms of TLS, of encryption, signatures, etc. All those things that we feel are super safe somehow are not going to be safe anymore, right? And you know, when we started to work with Frank, this Q day is like, okay, when is it? You know, so I've worked, as Srinath is saying, I've worked in security for 10 years now, and one of the factors of security is kind of instill a bit of fear in people of something, you know, something going to happen. So it's like, okay, I need a date. So if you tell people this is going to happen in 2050, they're not going to listen, right? So that date in the future, it's starting to get closer and closer and closer, right? Basically, that's what's going on. So the clock is ticking, right? And what should we really worry about this now is because that date in the future that was meant to be maybe 2040 or something like this, suddenly it's 2035 and now it's 2030 and maybe it's 2029. So like Q day is getting closer and closer and we feel like we're not really ready, right? So there's been a lot of developments in the past 6 months, a year, a lot of articles popping up on, hey, you know, what we thought will happen later is actually happening now. A lot of research around this. There's actually a very interesting research paper that came from Google that demonstrated as well that what we thought was necessary in terms of the power of those machines, of those quantum machines, the famous qubits, that Frank will explain in a minute, where we needed a lot of them. Now we're also seeing that we are needing much less of them to actually achieve that, you know, break those algorithms, right? And just like a few days ago, we had this news popping up saying the Shor algorithm can break a 5-bit elliptic curve key on this thing. So there's a lot on that title. Maybe this is what I'm going to turn to Frank on Shor bits, yes. 5 bits. What are we talking about here, Frank?
Yes.
In that title. What's hidden in that title?
What that means is, so 5 bits, so the number of bits in order to assess the strength of the key means how many operations 2 to the power of number of bits are needed to crack a key. And this means you need only 32 operations to crack the key, which is simple. So the only importance of this slide is people are working constantly on it, and here you can do it on a commercial computer. You can crack much stronger keys already, 48-bit keys. On a regular computer, we are doing that in my institute. I'm also working for a university. So this is coming damn close. This is the message here. People are constantly working on it, performing experiments. So the time that you have in order to protect yourself is very, very short. And Isabelle will explain you how short the time really is.
Indeed. And you could say, okay, so Q day is coming at some point in time. So why should I worry about this now? Like we're in 2025, you're telling me this is maybe happening in 2030. Why should I worry about this now? You should worry about this now because right now, all of you in this room, whatever industry, whichever industry you're working on, you're storing data at rest, which is encrypted, and therefore is encrypted with the current algorithm, the RSAs and ECC element of this world, right? So that data, the threat here is this harvest now, decrypt later, which means threat actors are gathering that information, even if it's encrypted. So today, they cannot look at it, but tomorrow, once they have the quantum computer, then they will be able to. right? So that's what we are doing. You know, there's a lot of information around this going on right now because of that specific aspect of it, which is, it's not because they cannot look at it now that they will not be able to look at it later, right? And why this is also matters, you see here on the screens, you have some dates on for how long do people need to keep data as well at rest. So depending on your industry, if you're in banking, if you're in insurance, if you're in healthcare, etc., you would have the obligation to keep information for a number of years, right? So this is the calculation that you have to do, right? You have kind of a critical action window now. So if you're storing data now and Q day happens before the time that this data elapses, basically, you're basically doomed. That's kind of the message, right? So that's why we're pushing this message and saying you have to worry about this, and encrypting the data now with quantum safe algorithms is because to make sure that once, you know, this happens and the famous Q day happens, well, you don't care because you're ready, basically.
Yes.
Right? So now this is coming the time where, what is a qubit,
Absolutely.
Frank?
So one of the power of the quantum computer that is underlying is the notion of a qubit. What you see on the left side is a bit. A bit has two potential values, right? It can be in state 0 or it can be in state 1. A qubit is very, very different. A qubit can be any point on this ball, on the surface of a ball. So the North Pole is false, the South Pole is true, and the qubit is always in a mixture. We call it a superposition between true and false. So it can be any point on this sphere. So there's an infinite number of potential values, which is one of the powers of a quantum computer. And the next slide shows that as you can bundle bits into a classical register, you can bundle quantum bits into a quantum register. So, and if you have n different n qubits, right? The qubits could be in state, everything is on the North Pole, 0, 0, 0, 0, or the first bit could be in state 1 and the others could be 0, 0, 0. So what you do is if you have n qubits, you have 2 to the power of n values at the same time in superposition. And if you want to simulate it, right, you can simulate quantum computing on a classical computer, but it breaks down very, very fast. Why? So, because if you have the number of atoms in the universe are known to be less than 2 to the power of 300, that means if you have 300 qubits, if you want to simulate a computation with 300 qubits, you need to turn each and every atom of the universe into a bit, which is obviously impossible. Such a huge machine does not, you can't build it, right? And what I'm doing is we are working with quantum computers that have more than 400 qubits, right? You simply can't emulate it anymore. And a quantum computer can manipulate this large amount of information in each single step. Each single step, a quantum computer manipulates data. This enormous number of information gets processed, right? This is the second power of the quantum computer, superposition, and now what's called here quantum parallelism. It's an inherently unbelievably powerful parallel machine. And the next slide then, shows there are algorithms, so many algorithms that are around are exponentially faster than classical algorithm, and one of the very famous algorithms that is important in our context is Shor's algorithm, and it basically can compute something that is here in the middle of the page, discrete logarithms. What the hell is a discrete logarithm? You don't need to understand it, but it can crack RSA, because RSA is the product of two large prime numbers. This is then the private and the public key. And if you can factorize a number in prime numbers, then you compute discrete logarithms, right? So factorization is one example of computing discrete logarithm. And Shor's algorithm can do that exponentially fast in polynomial time, extremely fast. While all known classical algorithms are exponential, right? So you can't crack RSA today because classical algorithms are slow running. And in fact, RSA 2048 has been invented because it will take the lifetime of the universe to crack a key with a classical computer. A quantum computer with, we say, 10,000 logical qubits can do it in a couple of hours. And even elliptic curve cryptography, right? It's also based on that the computing discrete logarithms is hard. It can be cracked in minutes to very few hours. So we are no longer safe when we have a quantum computer with 10,000 logical qubits. When I began to work on quantum computing 10 years ago, I thought, oh, this is beyond my lifetime. But the technology, as Isabelle already did indicate, is evolving so fast that many people who work in quantum computing believe it is early next decade, right? Where people like Microsoft are working on so-called topological qubit, whatever this means, and they say it may be time that 29, right? In 2029, we can crack RSA. IBM says they have 1 million of qubits, early next decade. So I would not bet that we need to wait for more than 10 years in order to crack keys, right? So it will be faster, which is important because most of the data, health data, for example, right? They need to survive and need to be kept secret for your lifetime, longer than 10 years, right? And harvest now, steal later means people are currently collecting data like hell, store it, and then they can crack it, right? And the rescue is what we call lattice-based cryptography. A lattice is shown here. These are the green dots. These are isolated dots in some vector space, right? And the lattice has a basis. What you see are the blue arrows. They span all the green lattice. You can multiply each blue arrow, right? And then you can add them so you can reach each of the green dots here. There's also another lattice, the red one. The red one is a very bad lattice because all computations in this bad basis are exponentially fast, terribly bad. So the blue arrows will become your secret key and the red arrow will become the public key so that you can't crack the public. So how does encryption work? So you use your blue basis to encrypt a message to result in the red dot. And then with the public key, you need to compute a lattice point close to the red point, and this is exponentially fast in classical computation, but in quantum computing, and also in quantum computing. So lattice-based security is the rescue because there's no known classical algorithm and no known quantum algorithm that can crack it. Of course, there is no mathematical proof that they won't be able to be cracked at all. And what happened is, the NIST, the American National Institute of Standards, has already standardized 3 algorithms. They wanted to standardize 4 algorithms, and on the day when they published 4 algorithms, a group basically presented a quantum algorithm that cracked the thing. This is why all cryptographic infrastructure that we need to build needs to be agile. You must be able to fast unplug an encryption, decryption algorithm and plug a new one in. So this is what's going on, standardization and so on. Isabelle.
All right. Okay. So now, thank you for the
Okay.
theory.
You or I?
I'll do the basis and
Absolutely.
you continue. Okay. So now we say, okay, we have to start now. Great, but you told us the computer quantum doesn't exist yet. So how do I start now? The good news is you can, right? But the approach to do that, though, is obviously not everyone is going to move from RSA, ECC, etc., to quantum algorithm from day one. So we need a dual approach, right? We need to be able to set up a system so that it can understand and use both, right? So whenever somebody talks to it and knows about quantum algorithm, it would use that. But if it says, sorry, I only know about RSA, it will do that as well, right? That's why we've taken that dual approach, right, Frank?
Yeah, so the approach is basically in order to allow you to gain trust in these post-quantum algorithms, you can apply, as Isabelle indicated, the classical and quantum algorithms in parallel. So you could sign, for example, a message classically, and then the signed message could then be signed based on a quantum algorithm. You can do it in series, or you can do it in parallel, right? You can encrypt data classically as well as post-quantum, for example. This is called the hybrid approach. And this is what most people implement. It's a hybrid approach in order to allow you to gain trust in quantum algorithms, and as long as you don't trust quantum, you still have, for example, a classical signature here, right? This is the hybrid approach that many people are basically doing. We at WSO2 did the very same. And what we are using, one example what we are using is, we are exchanging, if you establish a session and you want to exchange data encrypted with your partner, what you most efficient is a symmetric key. And what you do is you apply a key encapsulation mechanism. A key encapsulation mechanism basically takes an asymmetric key in order to encapsulate the symmetric key, send it to the partner, but the partner then unwraps the symmetric key, and then communication goes on with the symmetric key, because this is much faster than asymmetric encryption, decryption. This is key encapsulation. And what we are doing is we use key encapsulation based on a classical algorithm, public key RSA, yeah, and by ML-Chem. ML-Chem means it's module lattice-based encryption that we do. We do it also in parallel. It's a hybrid approach that we do in order to protect a symmetric key. Right? That's what we have enabled in our identity server and in Ballerina and so on.
We'll talk about that. And indeed, we were talking about new algorithms. All of them has been already defined and implemented as open source, which is great news.
Yes, and there is a consortium, Post-Quantum Crypto Alliance. They're all the biggies, right? Amazon, IBM, Google. They are actively working on the standardization of the algorithms. They're helping NIST, and they're also implementing the standardized algorithm. If you download the NIST post-quantum algorithm, you will be shocked. It's each algorithm 80 pages of pure mathematics. Even I was shocked. Pure mathematics, and these post-quantum crypto alliance, they implement it, right? They have a C library, and they have wrappers in different other languages like Python and so on, right, on top of it, and also Java. They are in GitHub repos. You can basically download, play around with it, and use them in your prototypes or even products to come up with post-quantum cryptography.
Now, when we started talking about this with Frank, and he started telling me, well, we'll have this dual approach and new algorithms, etc., what popped up in my mind is, okay, I know in standard crypto, the bigger the key, which is what themes we will be using here, as you see in red on the left, the bigger the key, the slower it becomes. If I have to use these very complex keys in every system, and it introduces a lot of latency, that is going to be a problem. But then we did some tests, didn't we? And we found that the results were amazing, right?
I didn't
Frank?
believe that, so I asked my colleagues to repeat the experiment over and over again, but it turned out that performance based on lattice-based crypto, on post-quantum, is not orders of magnitude, but factors faster than classical encryption, decryption. It was a shock to us, a positive shock for us, right? And the next slide shows the
back to our bits, right?
Go ahead, yeah. This is, so to speak, the number of bits that the security measurement, right, for how many security you get for operations that you basically perform. And here again, the post-quantum algorithms are much, much more efficient than the classical algorithms. Also something that blew our head apart, right? That's basically it, efficiency ratio.
So there's really no reason not to put this. It's easy to put in place.
Yes.
It's actually faster. It's more efficient. It will make you quantum safe. What's there to do, right?
Good deal.
All right. And actually, you may actually be using this already without knowing it, because in most browsers now, including in Chrome, for example, the default, like as I said, if you have that dual approach and the system finds it, by default, if it can talk to something using those new algorithms, it will actually do it out of the box. At the beginning of this setup, you actually had to turn some option on to actually do it. But now it actually works. And actually, you may have done this very easily before, because in our website, that's the way it's set up. So if you connect to our website in Google Chrome, you're already talking to our website and different things. in our, you can see here in this MLChem, right? It's using that already. So, okay, now that's a website. That's probably no crazy docs and information that we want to protect. But let's talk about regulations, and we'll come back to what we do at WSO2.
Okay. So the regulation basically in the US and EU, lots is going on in terms of regulation. So a couple of years ago, Biden legislation began to come up with a law that basically enforces all of the government organization to switch to post-quantum. The government organization basically needed to provide a plan by end of 25 how to achieve the transformation to post-quantum. In the meantime, Trump strengthened the standard. He speeded up to the end of this decade quantum safe, that each and every government organization must be quantum safe. And of course, industry is basically following. European Commission does the very same, right? In the US, so each of the member countries in the EU are transitioning to post-quantum. They have a standard called NIS2. NIS2 is also forcing companies, so they classified companies in essential, important, and the rest. Essential is food, energy, transportation, health, and so on. They need to migrate by the end of this decade to post-quantum. If they don't do it, the CXOs are under the gun. They need to, they become liable based on their personal money, right? So there's no insurance based on their personal money. They are liable if they don't move their company, and the very same is happening in the US. Cybersecurity Framework 2.0 says the very same. Even worse, even if you are a very, very rich CXO and you can pay the millions of bucks out of your pocket, right? The legislation says you will no longer be allowed to work as a manager in the EU and in the US if you are sued, right? So this is, if I speak in Europe and US about this, the CXOs get nervous, absolutely nervous, because now at the sudden they are under the gun. And what's not on the slide, that's the deadline. So NIST does the following. If you communicate with American companies, from 2030 on, RSA, ECC, and so on are depreciated, and after 35, you are no longer to communicate based on RSA, ECC, and so on. It's absolutely forbidden, right? That means even if you don't believe that post-quantum is something for you, you will be in less than 10 years no longer allowed to use that. If you communicate with European or American, and I'm sorry, I don't know about the Asian legislation here. Right? But in the Western world, you will no longer be allowed to communicate with Western companies if you are not post-quantum safe.
Absolutely. And so, what are we doing? Okay, so great. What are we doing to help them, right?
So,
Frank, that's the key thing.
Me? Okay. So what we started is we turned Ballerina into a quantum safe language. That means you can build applications based on Ballerina that are quantum safe, right? Communication between services or components are post-quantum safe. If you come from the outside to an implementation that you did with Ballerina, right, you can basically negotiate with the implementation that you only communicate quantum safe with it. Identity server is quantum safe, so we store all information symmetrically encrypted, quantum safe. Communication with identity server is also quantum safe, inbound as well as outbound, and more to come, right? So we are working on API manager and Choreo and so on, and turn that over the time to become quantum safe.
Absolutely.
And that's it.
That's it. Yeah, with only 5 minutes left. All right, so a conclusion a bit. We're gonna have a wretch of a conclusion in here, but the conclusion is you can do it right now, and you can do it with the WSO2 products.
I would rephrase it. I hope you're absolutely nervous. Go back to your business leaders and tell them that they are absolutely under the gun if they don't do anything, right? If they don't do anything, or you know it now, if you don't go to your managers and business leaders and don't say, we have a problem, right? Then maybe you at some point in time will be under the gun by your management team.
Call to action, basically. Okay, well, thanks a lot for your time.
Thank you.
It was useful. Thank you very much.
And be around.
Have a great afternoon.